In the previous video, I mentioned a bit of an oddity that occurs when we look at the massive carbon-12. We're going to have a look at that in more detail in this video, and we'll get to the idea of mass defect and binding energy. Now, the first point that I want to make here is that if we observe the mass of a nucleus, or if we were to say weigh the nucleus, so take it and pass it through a mass spectroscopy or mass spectrograph, we'd find that the mass of it is actually smaller than the sum of the mass of the constituent parts. So we get this very counterintuitive sort of situation based on what we know of mass and how it behaves. And when we're talking the constituent parts here, what we really mean is the nucleons. So as an example, we'll stick with the carbon-12 that we were talking about. So if we look at the mass of a carbon-12 atom, so I'm just going to write the symbol there in brackets, so mass of carbon-12, we saw from the definition that that's actually 12 atomic mass units. If instead, though, we looked at the mass of 6 protons and the mass of 6 electrons and added them together, we know that the mass of a proton is 1.007276, and we added to that the mass of 6 neutrons, with each of them having a mass of 1.008665, we would find that the total mass there comes out to be 12.095646 atomic mass units. Now you might look at that and think, well, that's not all that much, surely it's negligible. In this particular case, it is actually somewhat significant. So the difference that we see there, so the difference between the mass of the nucleus, or between the nucleus, nucleus's mass and the mass of the separate parts, or the total mass of the nucleons, we have a particular name for that, and as you can see in the heading, it's known as the mass defect. And we have a symbol for that. It's fairly straightforward one, just being delta M, so looking at the change in mass, or the difference in the mass. Now, that mass, we've got a difference there. What happens to it? We need to refer to probably the best known in terms of the equation itself. The understanding of it in the general population is not necessarily there, but Einstein's mass energy equivalence, like I say, one of the most famous equations, E equals mc squared, helps to explain what happens with this mass defect. So that equation tells us that the mass defect is converted to energy. So if you take those separate nucleons, they have a mass of slightly more than the mass of the nucleus together. So basically, if you were to sort of take them all separately and then squish them all together, that difference in mass is actually converted to energy. And this energy that we're talking about now is the binding energy. So the binding energy, we don't have a symbol for that, we just use the letter E, is the energy that keeps all the nucleons together. Hence the name binding energy. So if we can figure out what the mass of the nucleus is, we know what the total mass of the nucleons would be. We can figure that out quite easily. We can then figure out what the binding energy is. So if we do that so again, if we look at the example of carbon-12, we've already seen what the masses are that we're dealing with, so we can now find our mass defect. So that will be the difference between 12.095646 minus 12, so nice and easy, gives us the value of 0.095646 atomic mass units. If though we want to figure out what the energy is, we need to convert that to kilograms. If we're using E equals mc squared, we need to make sure we're in SI units. So we'd take that value of 0.095646 and convert it to kilograms, so that's using the conversion between atomic mass units and kilograms, multiplied by 1.661 by 10 to the negative 27. And you'll see here that the quantity of mass that we get, 1.589 by 10 to the negative 28 kilograms. So a very small amount, doesn't seem to be all that significant. However, when we look at the binding energy, we're going to now multiply that change in mass, or that mass defect, by the speed of light squared. So we have 1.589 multiplied by 10 to the negative 28, and we're going to multiply that by the speed of light, which is 3.00 by 10 to the 8, and keep in mind that these conversion factors, so this one here and the speed of light, they're in the data booklet, so you don't need to memorize them, you can just look them up. So that gives us a quantity of energy that's 1.43 by 10 to the negative 11 joules. Again, doesn't seem like much, but if you consider the amount of substance that would, the amount of atoms in a substance, very quickly can add up to be quite a lot of energy. Again, though, in joules, that small amount's not particularly easy to work with, so we're going to convert that to electron volts, and to do that we need to divide by the conversion factor for electron volts, so 1 electron volt being 1.60 by 10 to the negative 19 joules, and that then gives us a quantity of 8.94 by 10 to the 7 electron volts. A more common unit to use here is mega electron volts, so that would equate to 89.4 mega electron volts. So as I said, it's not a particularly large amount of energy for a single nucleus, but then when you start to add that up across a large sample, it can end up being quite a large amount of energy, and we'll see just how much energy can be released in some of these nuclear reactions as we go through. To take one last note here, the larger a nucleus is, that means that we've got more nucleons. So the more nucleons we have, that then means the harder it is to keep it together. And if it's harder to keep it together, that means there's more binding energy needed. And we'll see in class, when we go through and have a look at some of these problems, the binding energy does indeed increase for the larger nuclei. We'll do a couple of problems in class to have a look at that, and then have a look at some of the trends to do with the size of the nucleus and some of the other aspects about binding energy that are particularly important, that will then lead us into the nuclear reactions of fission and fusion.